Good morning. I'm Dr. E. Kavita, working as Assistant Professor in the Department of Chemical Engineering, SRM Institute of Science and Technology. I welcome you all for the lecture series on cleaner technologies and sustainability. So this is module 3, in which I'm going to brief you about clean technologies for power generation. Let us move on to the video. Module 3, Clean Technologies for Power Generation. So what are the contents in this Module 3? Environmental issues related to power generation, emission control in power plants, in that pre-combustion controls, combustion control techniques, and post-combustion technologies, clean power plant configurations, integrated gasification, combined cycle power plant, production of hydrogen. So what are the methods in that? Like steam reforming, partial oxidation, water electrolysis, and the reverse fuel cell operation, then direct thermal or catalytic splitting of water, and finally fuel cell, electrochemistry and thermodynamics of fuel cells, proton exchange membrane fuel cell, and the last topic, use of clean fuels. So in the first in the first part, I'm going to cover environmental issues, emission control, and the clean power plant configurations. Clean technologies for power generation. So this video covers the comprehensive overview of clean technologies and sustainability in power generation, tailored for postgraduate students. So this involves cleaner technologies for power generation involves promoting long-term environmental economic balance for the sustainable development, and also it enhances the energy usage to reduce the waste generation and also emissions. It utilizes renewable energy sources such like solar, wind, and hydro energy for clean energy, and it reduces pollution and preserves the available natural resources. What are all the environmental issues related with the power generation? Environmental issues from a cleaner technologies and sustainability perspective primarily revolve around human activities impacting natural systems. So these issues necessitate a shift from end of pipe solutions to prevent emission of pollutants as well as exploitation of available resources. What are all the key concerns involved in that? Resource depletion. Over extraction of non-renewable energy sources like fossil fuels and unsustainable use of renewable resources like deforestation or freshwater depletion. All these things leads to scarcity, increased cost, and also ecological imbalances. Then pollution. So it can be air pollution, water pollution, or soil contamination. So air pollution, this involves the release of particulate matter, sulfur oxides, nitrogen oxides, carbon monoxide, volatile organic compounds, and also other hazardous air pollutants from industrial processes, transportation, and also energy generation. So these pollution or the pollutants cause respiratory diseases, acid rain, and also contribute to climate change. Water pollution. This involves contamination of fresh and marine water bodies by industrial effluents like heavy metals, dyes, organic pollutants, agricultural runoffs, which involves pesticides, fertilizers. So that leads to eutrophication, and these impacts all these environmental pollutants impact aquatic life, human health, and also water availability. Soil contamination, accumulation of toxic heavy metals, hydrocarbons, and some kind of organic pollutants in soil from industrial waste, mining activities, and improper waste disposal affects the fertility of soil and also food safety. The biodiversity loss, reduction in genetic species and ecosystem diversity due to habitat destruction, pollution, climate change, over exploitation of resources, and invasive species. So this impairs ecosystem services vital for human well-being, and also which involves, I mean, which is essential for water, and also, I mean, water purification, climate regulation, and pollination, then climate change. Primarily, it is driven by anthropogenic greenhouse gas emissions. So these emissions trap heat in atmosphere, leading to global warming, extreme weather conditions, and also ocean acidification. So this is a transversal issue affecting all the other environmental concerns. The waste management crisis, so the ever increasing generation of municipal solid waste, industrial waste, and also hazardous waste, often exceeding some safe disposal capacities, leads to landfill issues, incineration challenges, and environmental contamination. So the shift towards a circular economy is a crucial point here. Emission control in power plants. So the power plants, particularly those burning fossil fuels, are the major sources of atmospheric pollutants. So emission control strategies are broadly categorized into pre-combustion techniques, combustion techniques, post-combustion techniques. So one by one, I'll brief you pre-combustion controls. So these methods aim to remove pollutants or potential pollutant forming components from the fuel before combustion. So which pre-combustion control method should be implemented? Fuel cleaning, upgrading. So in that, it enhances the fuel quality by removing the impurities, leading to cleaner production. So this involves coal beneficiation. There is physical and chemical processes to remove impurities from coal. Physical cleaning involves crushing and washing to remove ash-forming minerals and pyritic sulfur. Chemical cleaning, though less common due to cost, can remove some organic sulfur. Then also it involves desulfurization of fuel oil. Uh, Hydrodesulfurization is a catalytic chemical process where hydrogen reacts with organic sulfur compounds in crude oil or heavy fuel oil to form hydrogen sulfide, which is then captured. Next, fuel switching. So this reduces emissions by using cleaner fuels like natural gas instead of coal. So using inherently cleaner fuels like natural gas, which produces less sulfur oxides and particulate matter, or biomass instead of coal or heavy fuel oil. Coal gasification. So this converts coal into cleaner gas fuel, reducing the direct emission. I mean, this is a key pre-combustion control for coal. Coal reacts with a controlled amount of oxygen and steam at high temperature to produce synthesis gas, primarily carbon monoxide and hydrogen. So impurities like sulfur and particulates are removed from the synthesis gas before it is combusted rather than from the flue gas, making it a pre-combustion control. So this is integral to uh, integrated gasification combined cycle power plants. The next strategy, combustion techniques. I mean combustion control techniques. These techniques modify the combustion process itself to minimize the formation of pollutants, particularly nitrogen oxides. So what are the techniques involved in that? One by one, I'll brief you. Low nitrogen oxide burners. So these burners are designed to reduce flame temperature and oxygen availability in specific zones of the combustion chamber. Staged combustion. So air or fuel is introduced in multiple stages. Fuel-rich zones are created first to limit nitrogen oxide formation. In subsequent stages, more air is added to complete combustion. So this reduces thermal nitrogen oxides. Flue gas recirculation. A proportion of cooled flue gas, which is largely inert nitrogen and carbon dioxide, is circulated back into the furnace. So this dilutes the combustion air, lowers the flame temperature, and reduces peak oxygen concentration, thereby suppressing thermal nitrogen oxide formation. Over fire air. Air is introduced above the main combustion zone to complete the combustion of unburnt fuel, creating a fuel-rich zone in the primary combustion region and thus reduces nitrogen oxide formation. The waste or steam injection. Injecting water or steam into the combustion zone cools the flame temperature, which is effective in reducing thermal nitrogen oxide, especially in gas turbines. Fluidized bed combustion. Fuel is combusted in a bed of inert materials like sand or limestone, suspended by jets of air. So the lower combustion temperature, typically around 800 to 900 degrees Celsius, reduces nitrogen oxide formation. If limestone is used in the bed, it also reacts with sulfur dioxide to form calcium sulfate, capturing sulfur in situ within the combustion chamber. And next, post-combustion technologies, post-combustion control technologies. These are end-of-pipe solutions that remove pollutants from the flue gas after combustion. So particulate matter control. So what is it, particulate matter control? So this involves electrostatic precipitators, or application of electrostatic precipitators or fabric filters. The flue gas passes between electrodes. Dust particles are negatively charged and then attracted to positively charged collection plates, which are periodically wrapped to dislodge the dust into hoppers, so which yield higher efficiency for fine particulates. In case of fabric filters, flue gases passed through a series of fabric bags. So particles are captured on the surface of the fabric, forming a filter cake. Periodically, the bags are cleaned and then collected. Dust falls into hoppers. So this process is highly efficient, especially for very fine particles. Sulfur dioxide emissions control. So in that we have wet scrubbers, dry scrubbers. So in the case of wet scrubbers, flue gas is sprayed with a slurry of limestone or lime. Sulfur dioxide reacts with alkaline absorbent to form calcium sulfide or gypsum, which can be sold as a byproduct. So it produces high removal efficiency, nearly more than 90%. In dry scrubbers, alkaline solvent like lime is injected dry into the flue gas or a spray dryer, where it reacts with sulfur dioxide. So the resulting solid product is collected by a particulate control device. Less water consumption is involved in this process, but typically lower sulfur dioxide removal efficiency compared to wet scrubbers. And also, this kind of post-combustion control techniques could efficiently reduce the environmental impact by adhering to the regulatory compliance. Then this post-combustion control techniques also involves nitrogen oxides control and also carbon dioxide capture. These are advanced methods for reducing nitrogen oxides and also to capture carbon dioxide from power plant emissions. Nitrogen oxides control, so this involves selective catalytic reduction. So in that ammonia and urea is injected into the furnace at a high temperature, nearly 900 to 1100 degrees Celsius without a catalyst. So nitrogen oxide reacts with the reducing agent to form nitrogen and water. Um, but the efficiency of this process is a little bit less, and also there's a high potential for ammonia slip. And carbon dioxide capture, so this involves amine scrubbing. Flue gas passes through an absorber where carbon dioxide selectively reacts with an amine solvent like monoethanolamine. So the carbon dioxide rich solvent is then heated in the regenerator to release pure carbon dioxide, which can be compressed for storage or utilization. So this is the most mature post-combustion carbon dioxide capture technology. The other one, calcium looping, so which utilizes calcium oxide as a sorbent that reacts with carbon dioxide at high temperatures. The resulting calcium carbonate is then calcined to regenerate calcium oxide and release a concentrated carbon dioxide stream. So with this, the combustion control techniques like pre-combustion control techniques, combustion control techniques, and post-combustion control techniques are over. Next, we'll move on to integrated gasification combined cycle power plant, which is an advanced clean coal technology for sustainable power generation. This integrated gasification combined cycle. So what is that integrated gasification combined cycle? It is advanced clean coal technology that integrates coal gasification unit with a combined cycle of a combined cycle power generation system. It combines the coal gasification unit with a combined cycle power generation system. So this configuration allows for the removal of impurities before combustion, leading to significantly lower emissions compared to conventional pulverized coal plants. So the process overview. So step by step, let us see coal gasification. So in this, coal is fed into a gasifier where it reacts with a controlled amount of oxygen and steam at high temperature and pressure. So when it's a high temperature, it is around 1200 to 1600 degrees Celsius, and pressure is around 25 to 70 bar, such a high temperature and pressure. So this process, known as partial oxidation, does not involve full combustion. Instead, it converts the solid coal into synthetic gas, primarily composed of carbon monoxide and hydrogen, along with other impurities like hydrogen sulfide, ammonia, and also other particulate matter. So the reaction is coal with oxygen and water to produce carbon monoxide, hydrogen, carbon dioxide, and some impurities. Then the second part, syngas cleanup. So the raw synthetic gas is cooled and then passed through a series of cleaning units. So this is a critical advantage over other power plants, pulverized coal power plants, as a cleaning a pressurized syngas stream is more efficient and effective than cleaning large volumes of hot flue gas. And the third one, that involves gas turbine combustion. That is the syngas combustion. Syngas combustion drives a gas turbine generating electricity. So the hot exhaust gases from the gas turbine, which is around around more than 600 degrees Celsius are still very hot and contain significant energy. So that energy can be recovered, right? So heat recovery steam generator. So the hot exhaust gases from the hot gas turbine are directed to an heat recovery steam generator where they produce high pressure steam. Then the steam generated in the high recovery steam generator that drives the steam turbine generating additional electricity. So the integrated aspect refers to the efficient heat recovery. So the steam from the gasification cooling process is also often routed to the steam turbine, further enhancing overall plant efficiency. And in that, the optional part is water gas shift reaction. So what is that? If carbon dioxide capture is desired, syngas can undergo water gas shift reaction. I mean the reaction between carbon monoxide and water to produce carbon dioxide and hydrogen. So this converts carbon monoxide to carbon dioxide, increasing hydrogen content and making carbon dioxide easier to capture. And the carbon dioxide is then removed using physical absorption method. Then what are the key advantages of this system? Higher efficiency. I mean, the integrated gasification combined cycle plants can achieve higher electrical efficiencies around 45 to 50 percentage or more, potentially over 60 percentage with the advanced designs and hot gas cleaner compared to conventional plants due to the combined cycle configuration. Lower emissions significantly it reduces emissions of sulfur oxides, nitrogen oxides, particulate matter and mercury. So the pre-combustion removal of pollutants is more effective. Carbon capture ready, that is integrated gasification combined cycle is inherently well suited for carbon dioxide capture due to the high pressure concentrated carbon dioxide stream produced after the water gas shift reaction, making carbon dioxide capture more energy efficient than post combustion capture in pulverized coal plants. Then some more advantages: fuel flexibility. I mean, it can operate on various feedstocks, including different types of coal, biomass, and even municipal solid waste. Reduced water consumption. So it can have lower water consumption than conventional pulverized coal plants due to the gas turbines direct combustion rather than recycling solely on steam condensation. Next, what are all the challenges of integrated gasification combined cycle? Higher capital costs. I mean, this plants require huge initial investments compared to conventional pulverized coal plants. Operational complexity. There is the integrated nature of integrated gasification combined cycle plants leads to more complex operation and also it involves more maintenance. So these are all the challenges involved in integrated gasification combined cycle power plants. So conclusion. So I'm going to summarize this. So integrated gasification combined cycle technology offers a promising path for cleaner and more efficient power generation from coal, addressing environmental concerns while maintaining energy security. So with this, I am completing a part 1 of module 3. Thank you all for listening. Thank you.